everyone and welcome to Edexcel Combined Science Paper 2 walkthrough. And this is the 2018 paper, and I highly recommend that you go through the full paper with me, because if you gain a couple of marks on every single question, you will go up a whole grade. In question 1, we're told that the Earth's atmosphere contains several gases. Figure 1 shows the relative amounts of gases thought to be in the Earth's early atmosphere. So we had oxygen in small amounts, carbon dioxide in large amounts, nitrogen in small amounts, and water vapour in large amounts. The amount of water vapour in today's atmosphere is much less than the amount in the Earth's early atmosphere. Explain why the amount of water vapour in the Earth's atmosphere has decreased. So this is because the temperature around the world decreased. Therefore, the water vapour that was in the atmosphere then condensed and formed our oceans. The apparatus shown in figure 2 is used to find the percentage of oxygen in dry air. So we have syringe A, which contains 50 centimetres cubed of dry air, and syringe B, which contains no air. The copper in the glass tube is heated strongly. The air in the apparatus is passed backwards and forwards over the copper until the oxygen has been removed. The following results were obtained. So the initial volume of the air in the apparatus was 50 centimetres cubed. The final volume of the gas in the apparatus was 40 centimetres cubed. And we've got to calculate the percentage of the oxygen in the sample of dry air. So first of all, we need to work out how much of the air has decreased. So we have 50 take away 40, which will be oxygen part of the air, which is 10 centimetres cubed. So there was 10 centimetres cubed out of the 50 centimetres cubed of the original air that we had in syringe A. So to work that out as a percentage, it would be 10 divided by the original amount of air, which was 50, and then we multiply that by 100 to make it into a percentage, and the answer we get is 20%. Then, at the end of the experiment, the apparatus and its contents are allowed to cool before the final volume of the gas is measured. The apparatus and its contents must be allowed to cool because, and we've got to give the correct answer out of our 4 options here, and the correct answer would be because the gas has expanded when it's hot, so we need to leave it to cool, so we take the correct measurements. So for this question, we're told that the Earth's earliest rocks contained iron sulfide and no iron oxide. Later, the rock contained iron oxide as well as iron sulfide. Explain what happened to allow the change to occur. So over time, photosynthesis produced oxygen. So the percentage of the oxygen in the atmosphere increased. And because we have oxygen in the atmosphere, the oxygen will react with the iron, and the iron becomes oxidized to form iron oxide. Question 2a, a chlorine atom contains 17 electrons, 18 neutrons and 17 protons. State the mass of the chlorine atom. So the mass is the number of neutrons plus the number of protons. So that would be 18 plus 17, which equals 35. So the mass number is 35. Then for the second question, we are asked to give the electronic configuration of the chlorine atom. So chlorine has 17 electrons, which means it will have 2 in the first shell, and then the first shell is full. Then it would have 8 in the second shell, and the second shell is full, and we've had 10 electrons altogether, so we've got another 7, and the 7 would be in the outer electron shell. For part B, describe what you would see if we put damp blue litmus paper into chlorine gas. So here, the damp blue litmus paper would first turn red and then it would bleach itself white. For part C, chlorine is a diatomic molecule. In a molecule, 2 chlorine atoms are joined by a covalent bond. Describe what is meant by a covalent bond. So a covalent bond is a shared pair of electrons. So for this particular question, if you only put that it is shared electrons, that would only be 1 mark. You have to mention it's a shared pair of electrons. Explain why chlorine is a gas rather than a liquid at room temperature. So here, the chlorine molecules have weak intermolecular forces between them. And because the forces are weak between the molecules, only a little amount of energy is required to overcome them, which then means that the boiling point is low because you do not need a lot of energy to have the molecules moving around like a gas. When the gas hydrogen chloride, HCl, is dissolved in water, a solution forms. When we dip blue litmus paper into the solution, it turns red. State why the litmus paper turns red. So the litmus paper goes red because the solution has become acidic because it contains H plus ions. If you put that the pH is below pH 7, you would still get the mark here. Lithium, sodium and potassium are reactive metals of group 1 in the periodic table. Sodium metal tarnishes in air to form a layer of sodium oxide on its surface. 0.92 grams of sodium combine with 0.32 grams of oxygen in this oxide. Calculate the empirical formula of sodium oxide, and we're given the relative atomic masses, and we must show our working out. So first of all, we need to put the elements that we have. So we have sodium and we have oxygen. Then the first part is we write down the mass of each of the elements. So we have 0.92 and we have 0.32. Then the second part of the process is we work out the number of moles, because moles is mass divided by molecular mass. So if we divide the mass by the molecular mass, that would give us the number of moles. So we would have 0.92 divided by, and if we look at sodium, it's 23, which gives us 0.04 moles. And then we have 0.32, which was the mass of our oxygen, and the molecular mass of oxygen is 16. And if we calculate that out, we get 0.02. Now, we should be able to see when we're trying to put this into whole numbers, if we've got 0.04 as a ratio to 0.02, we actually have a ratio of 2 to 1. So therefore, our empirical formula is we are going to have 2 sodium atoms reacting and combining with 1 oxygen atom. So our empirical formula is Na2O. Now for part B, sodium reacts with water to form sodium hydroxide solution and hydrogen gas. Complete the balancing of the equation for this reaction and add the state symbols for each substance. So the brackets is for us to add the state symbols, and the dotted lines beforehand is for us to balance out. So if we look on the reactant side, we have initially we have 1 sodium on our reactant side and 1 sodium on our product side. Then if we go across to our waters, we've got 2 H2Os, so we've got 4 hydrogens on our reacting side, and we have 2 hydrogens as a gas, but 1 hydrogen in the sodium hydroxide. So to balance that out and get 4 hydrogens all together on the product side, we would need a 2 in front of the sodium hydroxide. Now, if we've got a 2 in front of the sodium hydroxide, we now have 2 sodiums. So we need to have 2 sodiums on our reactant side. So our sodiums are balanced, our hydrogens are also balanced. Now, if we look at our oxygens, we have 2 oxygens on our reactant side, and we have 2 oxygens on our product side. So the equation is balanced. Now, sodium is a metal, so sodium is a solid. so we put an S for solid. H2O is water, so that is a liquid, L for liquid. Sodium hydroxide would be dissolved in the solution, so that is going to be aqueous, AQ. And H2 is a gas, so that's a G for gas. So for question 3 part C, it says, in an experiment, equal-sized pieces of lithium, sodium and potassium are added to separate samples of water. A flame is produced only with potassium because potassium, and we've got 4 things to choose from, and the reason potassium produces a flame is because it's the most reactive, so it gives out the most amount of energy. So the answer there would be C. For part D, we're asked to explain in terms of electronic configurations the increase in reactivity from lithium to sodium to potassium, and this is a 2-mark question. So the first thing that we need to say is, as we go down the group from lithium to potassium, the atoms become larger, so the outer electrons are further away. And then for our second point, because the outer electrons are further away, they will be lost more easily due to there being less attraction to the nucleus. Now, in question 4, we are told that crude oil is a complex mixture of substances. Crude oil can be separated into useful fractions by fractional distillation. Figure 3 shows a fractional distillation column and the fractions being produced when a sample of crude oil is distilled, and we can see the different fractions on the right-hand side. The properties of these fractions vary from the top of the column to the bottom of the column. Which of the following is a trend in a property of the fractions obtained from the top of the column to those obtained at the bottom? So we're looking for the trend from the top to the bottom of the column. A says the average number of carbon atoms in the molecule present decrease. Well, that's incorrect because they increase down the column. B, the ease of ignition increases down the column. That's incorrect. C, the boiling points decrease down the column. That's incorrect as well. And the viscosities, the thickness of the fractions, increases down the column. So that's the one that is correct. Then for part B, most of the substances in crude oil are alkanes. Which of the following is the general formula for an alkane? And if you weren't sure, you could maybe draw out an alkane. So for example, I've drawn out butane here. So for every carbon atom, we can see that we have a hydrogen above, a hydrogen below. So however many carbons we have twice as many hydrogen, and then we always have our extra 2 on the end. So the correct answer is going to be D, which is CnH2n plus 2. So we've got to remember that we have those extra 2 on the end. Explain why alkanes are described as hydrocarbons. So alkanes are described as hydrocarbons because they are compounds which contain hydrogen and carbon atoms only. Now, if you don't put the word only at the end, you would only get 1 mark. So for the next part of the question, we are told that figure 4 shows a graph of the boiling points of some alkanes against the number of carbon atoms in one molecule of each alkane. So we've got the number of alkane carbon atoms in one molecule of alkane on the x-axis and the boiling points in degrees Celsius on the y-axis. And we have to explain the pattern shown by the graph. So the boiling points increase as the number of carbon atoms per molecule increase, and this is because with the longer hydrocarbon molecules, there are more intermolecular forces of attraction. When crude oil is separated into fractions, the amount of each fraction obtained rarely matches the demand for that fraction. Figure 5 shows the relative amounts of 6 of the fractions present in crude oil and the relative demand for each of these fractions. So cracking is used to match the relative amounts of a fraction of crude oil to the demand for the fraction. And the question is, use the information in figure 5 to give the name of the fraction that is most likely to be cracked. And that fraction we can see would be the fuel oil. And that's because if we're looking at the fuel oil, the amount that we get is much larger than the demand, so we can crack the fuel oil down into other fractions where the demand is higher. In a cracking reaction, reactants are heated to form products. The reaction is endothermic. On the axis provided, draw a reaction profile diagram of this reaction. Label the energy of the reactants, the energy of the product, and the activation energy. So first of all, we need to remember that our reactants are going to have less energy than the products because the actual particles will take in heat energy from the surroundings, so they actually end up with more energy. So if we draw our profile diagram would look like this, and we would have our reactants with less energy, our products with more energy, and the activation energy is going to be the total amount of energy that we had to put in. So if we draw a line across here, this amount here from our reactants to the top there is our activation energy. Then for the next question, we are told that dodecane to C12H26 can be cracked to form useful products. Complete the equation for cracking of dodecane by filling in the formula of the single molecule needed to balance the equation. So we've got to remember that according to conservation of mass, however many atoms you start with is the same number of atoms that you end with. Now, if we look here, we've started with C12. And if we look here, we are told that we have 3 C2H4. So 3 times 2 is 6. That means our molecule here must have 6 carbon atoms because 6 plus 6 is 12. And here we've got 3 times 4 hydrogen atoms. So 3 times 4 is going to be 12. So 26, take away 12, that means we are going to have 14 hydrogen atoms. For question 5, we are asked to describe what is seen when chlorine water is added to potassium bromide solution and the mixture is shaken. So chlorine water is a colourless solution to start with, and when it's added to potassium bromide, which is also a colourless solution to start with, the chlorine displaces the bromide and we get bromine in the water. So bromine water is then an orangey brown colour. So we will see that the colour changes from being colourless to an orange brown colour. Now for part B, chlorine reacts with potassium bromide to form potassium chloride and bromine. In this reaction, chlorine forms chloride ions. In this reaction, chlorine has been reduced. Explain using the equation how you know the chlorine has been reduced. So the chlorine has started off as chlorine atoms, so it has a 0 charge, and we can see that in the product it's a chloride ion, so it's Cl minus, which means it's gained 1 electron, and gain of electrons is reduction. Now in part 2, we have been asked to write the half equation for the formation of bromine from bromide ions. So if we start with bromide ions are Br minus. We are told we are going to make bromine. Now bromine is diatomic, so it's Br2, and if we end up with 2 bromine atoms, that means we must have started with 2 bromide ions. And for the ions to become atoms, they have to lose the electron that's on the ion. And because we've got 2 of them, we end up with having 2 electrons being lost. Aluminium reacts with chlorine to form aluminium chloride. Write the balanced equation for this reaction. So we start off with aluminium metal. We are going to react it with chlorine, which is Cl2, and we are going to produce aluminium chloride. Now aluminium is in group 3, so it's Al3+, and because chlorine is in group 7, that's Cl-, so that means we are going to need 3 chloride ions with 1 aluminium. So now we need to balance our equation. We can see that we have 3 chlorines on the product side and 2 on the reactant side. So a number that they both go into would be 6. So we try and balance it out with having 6 chlorines on both sides. So to get 6 chlorines on the reactant side, we would need 3 Cl2, and to get 6 chlorides on the product side, we would need 2 AlCl3 molecules there. Now, the aluminiums are not balanced, so I would need 2 aluminiums on my reactant side. For part D, a solid ionic compound is dissolved in water to form a solution. Describe a simple experiment to show that charged particles are present in solution. So here we need to describe electrolysis. So you would insert 2 electrodes, the anode and the cathode, which are attached to a battery or a power pack. We would also have either a light bulb or an ammeter connected to the actual circuit, and as the charged particles move around, we would either get a reading on the ammeter or the light bulb would light up. So for question 6, the rate of reaction between magnesium ribbon and dilute hydrochloric acid at room temperature is investigated. The apparatus used is shown in figure 6. The volume of hydrogen gas was given off, the volume of hydrogen gas given off was measured at regular intervals during the reaction. So we've got a diagram of the apparatus used. And then we have a graph in figure 7 which shows the results of the experiment. So we have the time taken in seconds on the x-axis and the volume of hydrogen gas collected in centimetres cubed. So our first question is, state a change that can be made to the apparatus in figure 6 to measure the volume of gas more accurately. So here what we would say is that we could use a gas syringe to measure the volume of gas instead of the measuring cylinder. A tangent has been drawn to the line on the graph in figure 7. Calculate the rate of reaction at this point. So to calculate the rate of reaction, we have to do change in y for the tangent divided by change in x. So from the graph, we can see that if we are trying to work out the rate of reaction where we have our line drawn on, it is the change in y divided by the change in x. So if we do the change in y, it's 43 take away 15, and then change in x, because we started at 0 and we went to 60, that would just be 60. And if we calculate that out, that gives us an answer of 0.47. So from the graph, we can see that we had 43 take away 15 for the change in y, and then 60 seconds for the change in x, which was the time taken. And that gave us a rate of reaction of 0.47 centimetres cubed per second. Now for part 3, on the graph in figure 7, draw the line that you would expect to obtain if the magnesium ribbon in this experiment was replaced with an equal mass of powdered magnesium, and all the other conditions are kept the same. So here the graph should be steeper to start with but finishes at the same place because the mass is the same. In part B, we have a balanced equation for the reaction. In another experiment, we're told that 0.1 moles of hydrochloric acid, HCl, were reacted with 0.1 grams of magnesium ribbon. calculate the number of moles of magnesium Mg in the 0.1 gram sample of magnesium ribbon. So to calculate the number of moles, moles is the mass divided by the molecular mass or the atomic mass. So here we would have 0.1 divided by 24, which is the relative atomic mass, and if we calculate that out, we get an answer of 0.0042. So we write our answer in here. Now for part 2, in a further experiment, 0.5 moles of hydrochloric acid were mixed with 0.5 moles of magnesium. Use this equation to show that in this experiment magnesium is in excess. So if we look at our equation there, we can see that 1 mole of magnesium reacts with 2 moles of hydrochloric acid. So what that means is that if we have 1 mole of magnesium, looking at our information here, if we've got 0.5 moles of hydrochloric acid, we then only needed half the amount, which would be 0.25 moles of magnesium to react with our hydrochloric acid because it's a 1:2 ratio. Two substances, A and B, each form a colourless solution. If the solutions are mixed in a beaker, A and B react to form a coloured product. The rate of reaction between A and B can be investigated by placing the beaker containing the mixture on a cross with a piece of paper and time how long it takes for enough colour product to be produced to make the cross invisible and viewed from above through the solution. So we have concentration of A in solution in grams per decimeter cubed. We have the temperature at which the 3 experiments are done, and we have the time taken for the cross to become invisible in seconds. And we are asked to use the results of these experiments to explain in terms of the behaviour of particles, the effect of changing temperature, and the effect of changing the concentration of A in solution on the rate of reaction. So first of all, if we compare experiment 1 and 2, we can see that the difference between experiment 1 and 2 is an increase in temperature for experiment 2. And if we increase the temperature, the particles have more kinetic energy, so they're going to move faster, which means the frequency of collisions increases. And as well as the frequency of collisions increasing, because the particles have more energy, they collide with more energy, so the rate of reaction increases. And we've got to remember that for a reaction to happen or a reaction to occur, the particles have to collide with the minimum amount of energy, which is the activation energy. So for the second part, where we are comparing experiment 2 and 3, we can see that experiment 3 has a greater concentration of A in solution compared to experiment 2. And if we increase the concentration, that means there's more particles in the same volume, there's less space between them, so the frequency of collisions increases, therefore the rate of reaction increases. Now, overall, therefore, experiment 3 has the fastest rate of reaction because compared to experiment 1, it has an increase in temperature, and compared to experiment 2, it has an increase in concentration. So therefore, it has a combined effect of the increase in temperature and the increase of concentration. Well done, we've come to the end of the past paper. Please do hit that subscribe button. By doing this, you will have easy access to more past paper walkthroughs, not just in chemistry, but biology and physics as well as topic learning that you may need help with. Also, if you have any friends that you feel this would be useful to, please do share my website with them, and I look forward to seeing you in some more science support videos.